You're listening to the Anesthesia Patient Safety Podcast, the official podcast of the Anesthesia Patient Safety Foundation. We're bringing you the very best from the APSF newsletter and website, as well as the latest information in perioperative patient safety. Thanks for joining us.
Hello, and welcome back to the Anesthesia Patient Safety Podcast. My name is Alli Bechtel, and I'm your host. Thank you for joining us for another show. We have discussed alarms on this show before when we've reviewed the article, Alarm Fatigue and Patient Safety, from the June 2019 APSF newsletter. Today, we are heading a little further back into the APSF archives to discuss one alarm in particular. To give you a hint, our featured article today is one of the top APSF newsletter articles of all time. Before we dive into today's episode, we'd like to recognize Acacia Pharma, a major corporate supporter of APSF. Acacia Pharma has generously provided unrestricted support as well as research and educational grants to further our vision that no one shall be harmed by anesthesia care. Thank you, Acacia Pharma. We wouldn't be able to do all that we do without you. Before we head all the way back to 1998 and into the archives, we are going to hear from the current chair of the APSF Committee on Technology. The low-pressure alarm represents an important link between technology and patient safety, and what better way to start the show than by hearing from Jeffrey Feldman. I'm going to let him introduce himself now.
Hi, my name is Jeffrey Feldman, and I am a professor of clinical anesthesiology at the Children's Hospital of Philadelphia and the University of Pennsylvania. I also serve as the chair of the APSF Committee on Technology and am a member of the APSF Board of Directors. I have been asked by Alli Bechtel to talk briefly today about the relationship between anesthesia patient safety and technology.
We are so excited to have Feldman on the show today. Let's take a listen to what he had to say about this intersection that was just as important in 1998 as it is today in 2021.
The simple fact is that technology is intimately involved with the safe care of every patient receiving anesthesia and sedation. Broadly defined, technology includes not only physiologic monitoring devices and anesthesia delivery systems, but tools for airway management, pharmaceuticals, infusion pumps, electronic medical records, and even disposables. From low to high resource environments, the anesthesia professional utilizes technology in some fashion during patient care. Understanding the capabilities and limitations of technology is essential for patient safety. The APSF Committee on Technology membership includes both clinicians and manufacturers of all aspects of the technology we use daily. The committee is dedicated to education on the safe use of technology and to identifying opportunities for improving technology to further enhance patient safety.
And with that, let's head into the archives. Our featured article today can be found by clicking on the newsletter heading. Fourth one down is Newsletter Archives. From here, scroll down to 1998 and click on the Winter 1998 issue. Looking at the articles column on the left, click on the fourth one down, which is our featured article today, The Low Pressure Alarm Condition, Safety Considerations and the Anesthesiologist's Response by David Raphael. As we go through this article, keep in mind that this is an article from our archives episode, so things may have changed since the publication of this article. This will just give us more to talk about on future shows, but this article is of interest from our archives. In addition, this is one of the top APSF articles of all time, so let's get into it. Have you heard or seen a low-pressure alarm in the OR while providing anesthesia care? The anesthesia machines are incredibly complex pieces of advanced medical technology. This was true in 1998, and it remains true today. When functioning appropriately, these machines provide oxygenation, ventilation, and anesthesia. When patients require mechanical ventilation, it is vital that the anesthesia machine and breathing circuit be functioning appropriately and be intact. If a low-pressure alarm occurs, this is the time for the anesthesia professional to take action to troubleshoot and address the alarm in order to be able to continue to provide mechanical ventilation to the patient. Now, it is standard practice that we have a continuous monitor and alarm for detecting breathing circuit disconnections, but this was not the case before 1986. It was in 1986 that the ASA adopted this as a basic monitoring standard due to data from a Harvard Medical School study by Eichhorn and colleagues. This study revealed that the creation and use of specific standards for mandatory patient monitoring during anesthesia care, which included a continuous disconnection monitor, could lead to improved patient safety and decreased patient injury. If you are interested in more information about monitoring standards in anesthesia, from the motivation to develop these standards, to the creation and use of these standards, to the current perspective about decreased patient risk during anesthesia care, check out the recent March 2021 article in Anesthesia and Analgesia, The Origins, Evolution, and Spread of Anesthesia Monitoring Standards from Boston to Across the World by Pandya and colleagues. I will include the reference in the show notes as well. If you have not read the article, the next little bit will be a spoiler alert. Pandya and colleagues conclude by highlighting 4 major themes that advanced anesthesia patient safety from the 1980s to today. Number 1, the use of closed claims analysis to identify areas of anesthesia care that were contributing to preventable patient injuries and thus needed to be addressed. Number 2, the introduction of the pulse ox as well as bedside capnography for improved patient monitoring. Number 3, the work done by the Risk Management Committee and the ASA to introduce the new monitoring standards and influence anesthesiologists to use these monitors consistently when providing anesthesia care. And finally, there was a push for reduced medical malpractice premiums from the insurance underwriters starting in 1988 as a result of incorporating these minimum monitoring standards into routine anesthesia practice. So let's move from minimum monitoring standards and get back to our featured article today, the low pressure alarm. First, what does this alarm detect? This alarm signals when the pressure in the breathing system does not meet a minimum threshold pressure in a certain amount of time, or very simply, when there is a loss of pressure in the breathing system. The low-pressure alarm may detect circuit disconnections, leaks, accidental extubation, fresh gas flow system failures, ventilator setting errors, obstructions within the anesthesia machine, and problems with the scavenging system. This is a pretty long list that anesthesia professionals may need to troubleshoot. Don't worry, we will go into more detail later. Even though the low-pressure alarm may sound when there is a circuit disconnect, it is not a designated circuit disconnect alarm. You may also be alerted to a circuit disconnect if there is a loss of the capnogram waveform or a zero-level reading on the spirometer or pressure trace. By using all the available monitors together, it helps to identify problems quickly and take the appropriate action to troubleshoot the alarms. Let's go into a little more detail about the types of low-pressure monitors, which may be different for different machines. We are going to discuss the examples that the author provides in the article. First, the DPM-S pressure monitor that can be found on the certain Draeger anesthesia machine systems can be found upstream of the inspiratory unidirectional valve in the circle breathing system, sounds the low-pressure alarm when the max pressure in the breathing system is less than the pressure threshold set on the minimum ventilation pressure switch for greater than 15 seconds. Another example is the Omida anesthesia machines, including the 7800 and 7900 series ventilators. The pressure monitor is located immediately downstream of the unidirectional inspiratory valve. For older machines, the pressure monitors may be freestanding or add-on features that are not turned on automatically and need to be set by the anesthesia professionals prior to patient care. The author makes a case that the low pressure alarm is the most important alarm, since it is more likely to alarm than the other anesthesia machine pressure alarms, including high, subatmospheric, and continuous pressure alarms. But it is important to be able to address all of these pressure alarms during anesthesia care to help keep patients safe. I mentioned that the location of the pressure sensing port may vary in the breathing system depending on the anesthesia machine. Despite the variability, the location of this monitor is important to create an accurate differential diagnosis and ultimately address the alarm. The ideal location is close to the Y piece that is connected to the endotracheal tube and very close to the patient's airway. This is not where the pressure monitor is located, though, because in this location there's often a buildup of condensation and risk of contamination from the patient's secretions, which would prevent the monitor from functioning adequately. As a result, the pressure monitor is located further away from the endotracheal tube. Another important area that we need to discuss related to the low pressure alarm are false negative situations. This may occur when there is a real low pressure condition in the breathing circuit, but the low pressure monitor fails to alarm. This may be a cause for alarm, so let's talk about why this might happen. It may fail to alarm because the threshold criteria for the minimum pressure was reached at the location in the breathing circuit of the pressure monitor. Thus, the most common false negative situation is when the anesthesia professional does not set an appropriate minimum pressure threshold. If the minimum pressure threshold is set too low, then the monitor may fail to detect a partial disconnect. What does this situation look like in clinical practice? There may be a partial obstruction of the breathing circuit at the same location of the partial disconnect, and as a result, the pressure in the breathing circuit will be lower, but it will not fall below the threshold, and there will not be an alarm, and the partial disconnect may go undetected. To prevent this situation, make sure that the low pressure threshold is set just slightly below the maximum inspiratory pressure. There are other clinical situations that may lead to a false negative. Let's go through them now. Occlusion downstream of the pressure sensing port. This will lead to low pressures distal to the occlusion and high pressures proximal to the occlusion at the pressure sensing location. As a result, the low pressure threshold will not be met, at least not immediately. Occlusion of the Y piece that has been disconnected from the pressure circuit, which allows the pressure in the breathing circuit to remain above the minimum threshold. This has been reported due to the patient's pillow obstructing the breathing circuit. This next situation has been reported in the past with the North American Draeger Narcomed 2 and 2A anesthesia machines with the AVE ventilators. The false negative may occur when very high inspiratory flow rates are used, leading to a compression distortion of the bellows during the inspiratory phase of the cycle, which then leads to a generated pulse pressure and small gas flow, which can maintain pressure in the breathing circuit above the threshold, even if there is a complete disconnect. Buildup of back pressure in the breathing circuit by a humidifier that has been added to the circuit may prevent the low pressure alarm from alarming during a disconnection event. With the use of descending bellows, in this situation, the bellows will continue to fill even if there is a fresh gas flow disconnect, since ambient air enters the bellows during exhalation. And finally, alarm malfunction or failure to turn on the alarm. Despite the huge benefit that occurred for patient safety with the addition of the low pressure alarm, this is not the time to let down our guard because false negative situations can occur. We can continue to work to keep patients safe by staying vigilant and monitoring additional parameters, including capnography, or by physical exam and listening to breath sounds, or the use of an esophageal or precordial stethoscope. There is still so much to talk about with the low pressure alarm, and next week we'll be back to review the differential diagnosis and take you through a response algorithm with practical steps to follow in case you hear or see a low pressure alarm in the OR. Before we wrap up for today, we are going to hear from Feldman again. This is the perfect way to move out of the past and back into the future.
Thank you, Alli, for reviewing this interesting article from the APSF archives. To conclude this podcast, Alli has asked me to offer a perspective on the future of technology for enhancing patient safety during anesthesia care. The technology we use today has undoubtedly made patients safer and is truly nothing short of remarkable. Pulse oximetry and capnography alone have prevented numerous patient deaths and injuries, and are inexpensive enough to be made available to the overwhelming majority of patients who receive anesthesia care. That said, the technology environment is not well integrated. Multiple devices are completely independent of each other, sometimes even from the same manufacturer, leading to confusing displays, unprioritized and distracting alarms, as well as different methods of control. This poorly integrated technology environment increases the risk of errors of various types, both commission and omission. Clinical decision-making at the bedside is challenged by the fact that information is not displayed in a useful fashion. Improving the current technology environment will require integration and design based upon sound principles of human factors engineering to reduce the chance of error and enhance clinical decision support in the acute care environment.
Thank you so much to Feldman for his contributions to the show today. It will be exciting to see improvements in technology and especially steps taken to integrate the technology environment for anesthesia patient care going forward. If you have any questions or comments from today's show, please email us at podcast@apsf.org. Visit apsf.org for detailed information and check out the show notes for links to all the topics we discussed today. Please keep in mind that the information in this show is provided for informational purposes only and does not constitute medical or legal advice. Have you checked out the June 2021 APSF newsletter yet? It was published online on June 1st. Go check it out, and don't worry, there is some great content that we will be discussing in upcoming shows. Until next time, stay vigilant so that no one shall be harmed by anesthesia care.